Okay, you guys are lame. Porter Podcast, and we're going over macro review number 3, which is over the quantum mechanical model. You guys remember that? Electron configuration?
The one
Electron configuration, battleship.
Oh, yes.
Yeah.
Okay, perfect. So, couple things here. One, when it's asking to diagram the 1s and 2p orbitals, your test question is literally going to have a three-dimensional plot. An s orbital looks like a sphere, so this is S. A p orbital looks like what? Anybody? No. P orbital looks like a peanut. So, there's an S, there's a p orbital. You guys recall that?
I don't remember any of that.
I don't recall that.
So, around the nucleus, so if the nucleus is the origin, right? Yeah, let's just draw one with all of them. So let's just say our origin is the nucleus of the atom. We are looking with the quantum mechanical model where electrons fill in around the nucleus. So we have three-dimensional spaces where electrons are likely to preside. So those three-dimensional spaces are called orbitals. So your 1s orbital looks like a sphere. That's where you're likely to have your first two electrons. Your 2s orbital also looks like a sphere, but a bigger sphere. Once we get to the 2p, we have three 2p orbitals. We have a 2px, we have a 2py, and we have a 2pz. All of these are spaces around the nucleus where electrons most likely preside. Now, all the orbitals stack on top of each other. So electrons are just getting further and further from the nucleus, the more electrons that we have to fill around the nucleus. Does that make sense? So this is all clustered up, but you basically just need to know what an s orbital looks like and what a p orbital looks like. S and p. All right. So I'll erase that. That's number 1. Skip number 2. Let's go to number 3. Explain through the off-ball principle, Hund's rule, and Pauli exclusion are explained through drawing the off-ball principle. So, off-ball principle says what?
Isn't that like you have to go 1s and then 2s?
There you go.
And then
So,
2p.
1s, 2s, 2p, 3s, 3p, 3d, 4s, so forth and so on. So the off-ball principle says lowest energy sublevel first before going to the next one. So you have to fill in the 1s, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, followed by the 3d, 4p, so forth and so on. So when we talk about the full electron configuration, that's where we get it, the off-ball principle. Hund's rule is when we start getting down into the individual orbitals. So D has 5. So if we have 3D, Hund's rule says we fill up each of these 5 orbitals, 3D orbitals, with 1 electron before going back and doubling up with a second electron.
Do you always do the top arrow first?
Yep, always do spin up first and then followed up by spin down. Pauli exclusion principle simply states that electrons in the same orbital have opposing spins. That's why we represent them with a spin up arrow and a spin down arrow. Right? Spin up electron, spin down electron. That's Pauli exclusion principle. Alright, that's number 3.
What about the quantum numbers, the 4 numbers?
We can do an example of that here at the end.
Okay.
So, chromium and copper, write the full electron configuration, and then we're going to move on and write the noble gas configuration after that. So, full electron configuration for chromium, what does it end on?
24, so it ends at
D.
AR and then B.
Should end on 3D4. So, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now, you need to recall that this is one of the exceptions, the half whole rule. So I'm going to borrow 1 from the S, make it 4s1, and put it in the D to have 3d5. So if I'm going to do number 5, that means I'm going to take my 1s2 through 3p6. I'm going to replace that with the noble gas, argon, and then write the rest of my electron configuration, 4s1, 3d5. If I draw the noble gas, or if I draw the orbital diagram, 4s, spin up, 3d, 5, spin up, spin up, spin up, spin up, spin up. There's your orbital diagram. Hey, quiet down a little bit. It's getting a little loud. All right, so that is everything for chromium. Let's do copper. Copper ends on what?
29.
3d9.
So 3d9, but remember, instead of 3d9 and 4s2,
It's 3d10 and 4s1.
it's going to be 4s1 and 3d10. So that would be copper with spin down, spin down, spin down, spin down, spin down. All right, so there's copper. So there's 4, there's 5, there's 6. Why do these exceptions exist? Half whole rule. There is 7, and you guys requested quantum numbers, so the last electron filled in here was this one.
Isn't that
So,
negative?
our yeah, but let's go in order. Our 4 quantum numbers is energy level, 3, sub-level, which is D, equals what? S equals 0, P equals 1, D equals 2. What orbital are we in? 0, plus 1, plus 2. So we're at positive 2, and our spin is
Negative.
Negative.
negative 1/2. So there's your 4 quantum numbers for that one electron.